The broadcast is now starting. All attendees are in listen-only mode.
Welcome everyone. This is Jim Chastain with EasyPower, and this is our Thursday technical presentation. And before we introduce our guest speaker, I wanted to welcome everyone and run a couple poll questions to get a little bit of feedback. I appreciate your attending today, and obviously there's no obligation as far as these polls, but they do help our presenter understand the audience a little bit. So let's kind of preview what they're going to be. Mainly, it's trying to get some feedback on your exposure to the topic. So if you would please participate by giving us some feedback, we would appreciate it. It looks like we got a pretty good participation rate. Here's how, and interesting enough, we ended up 50-50 on it. So, all right, the second question is, have you looked into the ABB's ultra-fast earthing switch before? All right, looks like we've got a quorum here. Thank you. And overwhelmingly people are, I think, attending because they have an interest in it. And then, is anyone actually considering using an active arc flash solution? All right, looks like we got close to 80%. Here's how people have weighed in on this. What type of systems do you normally work with? And usually we only have 2 or 3 questions, so I apologize if this is taxing for anyone, but we do appreciate your feedback. So what type of systems do you work with in your normal sphere of influence? Looks like we need this for about another 5 seconds. All right, thank you. All right, looks like we have a well-rounded audience. And then finally, and this one is fascinating, especially with my concern or my interest, what type of market segments do you think this type of technology would be useful in? And again, it's a system that has a lot of applications, and it's the audience I think will have as good an understanding on this as anyone. Excellent, thank you. Here's how folks weighed in on this. So it looks like we have representation across the board. So let me introduce our guest speaker. Kansu Yildirim joined ABB in 2016 and has worked as a project manager for fault current limiting solutions before starting her role as a business development manager for distribution systems in Germany. She's part of a team of technical experts who are responsible for the global sales and marketing of fault current limiting solutions, active arc fault protection, and fast bus transfer solutions. Kansu holds a Master of Science in Business Administration and Engineering from the prestigious RWTH University in Aachen, Germany. And with that, let me give the controls over to Kansu. It's all yours, Kansu.
Okay.
Share your screen with us. Thank you. Looks great.
Okay, thanks. Thanks for the interaction. Hello, everyone. This is Jansu speaking from ABB Germany. Thanks all for participating and joining today's webinar on active arc flash mitigation solutions. Our today's session is going to be about ABB's UFIS ultra-fast earthing switch and active internal arc protection system. Please feel free, in case of questions or additional information, to reach out directly to me. We will have at the end of the session a short Q&A, but we will also try to answer your questions afterwards. So here you can see my contact details. Here's a short overview about today's agenda, where I will start the session with a short introduction into internal arc faults, followed by different protection concepts, and then introduce you the UFIS, its principle and its components. Give a short overview again about the differentiation of protection concepts, our product folio and its benefits. And last but not least, I believe that might be the most interesting part for you, different application examples for different industries. So I'd like to start with a short video. I need to warn you here, it might become a bit noisy in the video. So here we're going to see an arc fault demonstration with a 4 kE 4 current done in our test lab in Ratingen in Germany. So there we go.
Okay, ladies and gentlemen, the demonstration will start in 3, 2, 1, go.
So what you could just see was an arc fault. In general, the occurrence of an arc fault is the most serious fault within a switchgear system, and is mostly associated with extremely high thermal and mechanical stresses in the area concerned. There we had it. An internal arc arises when at least part of the current passes through a dielectric, usually air, such as in the example which we saw in the previous video. The consequences could be or usually are uncontrolled release of energy with an arc power up to 40 megawatts. Also, what you could see is the arc plasma with temperatures up to 20,000 Celsius, which is 5 times of the sun surface temperature. A rapid pressure rise inside of the switchgear if you're having a metal enclosed compartment, depending on the design, also in the environment, and light with illuminance more than 20 times higher than the typical office light. High acoustic stress levels, as we could all hear, explosive release of plasma, fragments, and toxic gases, which might be, which are quite dangerous for everyone working in a switchgear environment. On the right-hand side, what you can see here is the energy release for cable fire, copper fire, and steel fire, and the arc fault is even above of all of that, what we can see here. What are the typical causes for internal arc faults? Most of the times it's human-related causes. It could be staff working on energies equipment, intended or unintended, disregarding the 5 safety rules. Unfortunately, in many countries, safety is not the highest topic. Left tools after working equipment, installation faults such as in cable connections or busbar joints. Another reason could be the technically related causes such as aging and wear, defect devices, over voltages, over temperatures, or environmental causes, which can be moisture and dirt, corrosion, small animals inside of the switchgear. So, as we've just mentioned, the effects, an internal arc fault is characterized by a rapid temperature rise up to 20,000 Celsius. This causes a chain reaction of other hazardous impacts. Users would like to prevent system components from being destroyed And of course, the absolute protection of the personnel is by far the most important concern during an arc fault. So the rapid temperature rise results in rapid pressure rise and the melting and sublimation of metal insulation material, which then again leads to release of plasma and particles and hot gases. And the consequences are heavy damages inside of the switchgear for the integrated devices and for the building, and heavy injuries for your personnel possible for switchgear systems without internal arc classification. So here we see a video. The video you've just watched presented a typical behavior from an arc accident in an actual test performed by ABB. That was an internal arc test for 50 kA 1 second. Fault initiation was in the circuit breaker compartment. And in very rare cases, the failure inside a switchgear cubicle due to effect or an exceptional service condition or maloperation may initiate an internal arc, which will lead to extreme impacts from for the inside of the switchgear and for the integrated devices. As you could see here, that was an explosion of the panel itself. So here we can see some pictures showing the effects or the impact on the circuit breaker, completely melted and destroyed, and the switchgear after an internal arc impact. Here we can see a substation before an arc fault and the leftovers after an arc fault. So let's have a look at different protection concepts. In general, there are three kinds of protection concepts. One of them is the passive internal arc protection, which most of you might know. Here you would use a pressure relief duct or tap chimney in order to relieve the hot gases outside the switchgear room. This is a typical application where customers do not have ITH limiters, or where there is no differentiation between internal and external faults possible. The arc faults are covered by the overcurrent protection of conventional protection relays. However, what you can see here is that for a passive arc fault, protection with gas ducts, and the fault happening here in, for instance, the cable compartment, the hot gases are going up to the top to pressure relief duct, and then the gas duct takes away the hot gases outside the switchgear room. Another option is the top chimney, where you have, again, for instance, an arc fault happening in the cable compartment. Hot gases are directed to the upper part of the panel, and the top chimney then reduces the pressure and cools down the hot gases. However, for this kind of conventional protection approach, the fault detection is done by a standard relay, and the clearing of the arc fault itself, arc fault current itself, is done by the upstream circuit breaker. So usually we are talking here about a minimum time for the arc breaking of 100 to 1000 milliseconds, which consists the setting of the protective relays. Depending on the setting of the protective relays, the switching time for the circuit breakers plus the arcing time for circuit breakers. So that might be already too late for your system to overcome such a harsh fault. A second protection concept would be the active internal arc breaking. Here we have a fast-acting protection relay with supplementary equipment like the ETH limiter. We have a fast detection of an internal arc fault, typically light sensing and instantaneous current sensing. And here again, the clearing of the arc fault is done by the upstream circuit breaker. So usually you have a detection time plus a circuit breaker switching operation time plus a circuit breaker arcing time, which leads to 60 to 80 milliseconds. As a third option, we have active arc elimination, such as the UFIS. Here we have a primary switching element, like as you can see here. We have a fast arc detection relay. And what's happening here, we have a fast detection of an internal arc fault by means of light sensing and instantaneous current sensing. The arc elimination itself is done by means of ultra-fast short circuit earthing with a specific primary switching elements, which are here. So here you have the fault detection and then the signal triggering, leading the primary switching elements to eliminate the arc. Here we are typically talking about an arc elimination time of 4 milliseconds after detection. Switching open again. So let's have a closer look at the UFIS, its principle and its components. The UFIS consists three primary switching elements, which you can see here in a reddish orange color on the right hand side. Those are responsible for the ultra-fast initiation of a three-phase earthing immediately after detection of an internal arc fault, and the elimination of the arc in consequence of the arc voltage collapse. The signal, the tripping signal for the primary switching elements are given by the control units. There we have two types of control units. One of them is the QRU100, which is equipped with its own detection units, light and current sensing, to identify an internal arc fault. And the other one would be the QRU100 with an interface to external arc detection system, for instance, with which can be combined, for instance, with ABB RIA system or with other units. In this control unit, we have the energy storage for the tripping of the UFIS PSE is to trip the primary switching elements. So how is that working? In the tripping of the ultra-fast earthing switch, first of all, requires a rapid and reliable detection of an arc fault in a defined protection zone of the switchgear system. So here you see one feeder solution where you have, let me get the spotlight again, the UFIS, a tripping unit, and the detection unit for current and light sensing. Here you have the circuit breaker. Assuming that you have a fault here, let's have a look what's happening. The specific fault is detected either by an external arc fault detection system, which is combined with a UFIS electronic tripping unit, type QRU100, for instance, or alternatively by an expandable UFIS electronic detection and tripping unit, type QRU1. If a specific criteria or condition for tripping is fulfilled, the UFIS electronic issues a trip signal to the three primary switching elements, which then again establish a three-phase metallic short circuit at the point of installation. So as this short circuit is of considerably lower impedance than the fault current commutates from the arc to the defined short circuit created by the PSE, causing the arc fault voltage to break down and the arc to be extinguished almost immediately after tripping. So, and the rest is actually clarified by the upstream circuit breaker again. Here we can see the occurrence of a short circuit fault. What we see here is that the extinction time for the UFS is even below the short circuit reaches its peak. So we have less than the reaching time for the tripping criteria plus the 4 milliseconds after fault detection. Here we can see a cross-section view of the primary switching elements. What you can see here is, first of all, here you have the UFS primary switching element itself has a epoxy insulator on the outside, a fixed contact, there you go, a ceramic insulator, a moving contacting pin for the earthing later on, and a piston, a cylinder, and a moving contact system, and a micro gas generator. So the chamber actually consists 2 vacuum gaps separated by a membrane. One gap contains a contact pin at earth potential, while the other accommodates a fixed contact at high voltage potential. Each primary switching element features an interrupted ultra-fast microgas generator. For the switching itself, it's actually comparable to a gas generator in automobile airbags. And after detection of the arc fault, at almost the same time, the gas generator is activated, and more specifically, let's move to the next slide, and you can see it in a better way. And the gas pressure drives the movable piston, which is on earth potential in its initial position, into the fixed contact socket, which is on the busbar potential, and that one creates a solid metal short circuit to earth. So here you can see how the current flow is after tripping. And after the operation of the primary switching elements, since this is a one-shot device, the primary switching elements needs to be exchanged. Having a look at the 2 control units, here we can see the QRU1, which is detection and trapping unit within one device. It's completely analog technology, so there is no microprocessor. It has 9 optical inputs for light detection and 3 current inputs for the monitoring of the instantaneous current value. In combination with a ABB's arc guard type TVOC2, it can have up to 150 additional optic inputs, and that needs for the fast localization 1 single lens sensor. It is self-monitoring and can be tested, so it has a functional test check option, and is based on a simple dip switch configuration. Here we can see an example, an installation example of the UFS QRU1 with the TVOC2. Here you would have in the first panel the primary switching element together with the UFS control unit, and the TVOC in one of the other panels with its respective optical inputs leading to the different neighbor panels. The arc flash event is transmitted via hardwire tripping cables to the QRU1, and the overcurrent detection is done by the control unit itself. And as previously mentioned, the control unit trips the primary switching elements after it detects an overcurrent and an arc, or it receives an arc detection signal. The arc elimination is, as mentioned, in less than 4 milliseconds after the detection. The other option would be the UFS electronics type QRU100. That one is an electronic tripping unit only. It's ideal for complex systems and for an extension of ABB's arc detection systems, the RIA family. It has 2 Optolink inputs for the connection of the ABB RIA 101 relay, 2 high-speed inputs for the connection of external arc detection systems. is self-monitoring and has also a logic combination of the external detections units by the use of dip switches. That one also has a testing mode for functional checks. Here we see also another installation example. It's similar to the previous one with the difference of that one is just a Curo 100 and in combination with the RIA family. So let's have a look again at the different protection concepts. So we've been talking about the three protection philosophies: the conventional protection, the fast protection, and with the help of a relay, and the ultra fast detection with the UFAS. Here on this graph, what you can see is the energy development over time in case of an arc fault. What we're seeing here is that for conventional protection devices, the energy level develops in such a way that you will have dramatic consequences on your equipment. There will be fire, explosions, hazards, as we could see in the second video, which I showed you. There might be, or hopefully there won't be, which is still possible, heavy injuries of your personnel, depending on the switchgear design. The other one, the fast protection relay concept, has limited consequences for your equipment and personnel. However, that one compared to the UFAS is still leading to an energy development and a way too slow compared to the ultra fast earthing switch type, where you don't expect any consequences on your equipment, and the energy and the thermal damage level will be decreased drastically, and there won't be that high of a pressure rise. Here I wanted to show you again the overpressure development for an arc fault current occurring for a 50 kA RMS and 130 kA peak for a switch in a switchgear with and without the UFAS. Without the UFAS, you can see that there is an overpressure of up to 1.65 bar, whereas with the UFAS, there's even less than half a bar pressure development. What we can see here is some pictures and the impact of an internal arc without the UFAS and with the UFAS. Without the UFAS, you can see clear signs of the arc fault on the left-hand side, in your panel and inside and outside your panel. Whereas with the UFAS in the busbar compartment, there is no signs. Only there's just a footprint at the point of fault initiation visible of the arc fault. So as you can see, the damages are way much more reduced comparable to the application without the UFAS. Here on this slide, I wanted to show you again how the pressure is rising in a room, in a switchgear room where you have the UFAS or where you don't have the UFAS. As you can see with the UFAS, it's way below compared to the installation room without the UFAS. So here's again a video for you. Let's see what happens if we have a UFAS installation. Here again, we see the arc fault without the UFAS, which you saw in the beginning. And now let's pay attention to the primary switching elements on the bottom. So as you can see, no drastic signs of an arc fault with the help of the UFAS. having a look at our product portfolio, we can see typical ratings for our primary switching elements. The maximum available rated voltage for application for our UFS applications is 40.5 kilovolts. For the medium voltage level, for up to 70.5 kV, we have up to 50 kA for 3 seconds and 63 kA for 1 second. For low voltage applications, for short circuit withstand capability of 100 kA for half a second, we have a rated voltage of 1.5 kV. Usually the UFS for as loose components comes in a kit solution. This is a popular solution for OEMs. The UFS kit comes either with the QRU 100 or the QRU 1, always with one set of tripping cables and a set of primary switching elements. So particularly for older non-IEC qualified switchgear systems, the UFS allows the highest degree of protection for your equipment and operator safety. And we have a variety of solutions for retrofitting of existing switchgear systems, since there might not be always the option of upgrading or exchanging a complete system. Here you can see one of the retrofit solutions we have is a service box. That one goes up to 24 kV. It's for the retrofitting of air-insulated switchgears, for instance, and it gives you a maximum installation flexibility to suit your space requirements. Another solution we have is a withdrawable truck solution. And here the UFS primary switching elements, the PSEs, are installed in a withdrawable assembly or truck design. It provides you the opportunity to upgrade the existing switchgear, which does not necessarily have to be an ABB panel here. The contact with the busbar is established via the isolating contacts of the withdrawable assembly, and within an optimum plug-and-play solution, you can here again upgrade your system, and it's similar. We have similar solutions available for other switchgear types upon request. So feel free to reach out to us if you have a specific question here. Another popular solution here is the UFS installed in a top box on top of the panel, or typically in the cable compartment, which you can see on the right-hand side. Also popular is the UFS as a transformer protection used in or installed on the primary side of the transformer, which you can see here on the right-hand side. Our product is UL recognized, so that's I assume most of our audience is from the US, so this is actually one of the most important certifications for you. The other one, I saw in our poll at the beginning that we have some of our participants are interested in marine applications. The product is also DNB GL certified, and for the German market we have a VDS certification. So offshore as well as onshore certified. Let's have a look at the benefits of the product. We've been talking about the impacts of an internal arc fault. So we've been saying that one of the major effects is the rapid temperature and pressure rise, the release of hot plasma, and the secondary effect would be the visual and acoustic load for persons, such as in the first video, and the development of explosive hot toxic gases. So to sum it up, The UFS provides increased operator safety, reduces repair costs, reduces downtimes, and provides a solution for locations with limited pressure relief opportunities. Here again, we have a comparison of the three concepts we've been talking about. As you can see, whereas all of the three concepts fulfill the requirements for personal safety, more or less, and under normal operating conditions, or the building protection, compliance to legal safety regulations. The first two, the passive protection concepts, start failing when it comes to minimizing mechanical and thermal impacts on the equipment, when it comes to pressure sensitive environments, or to increasing, or when it comes to system availability. So one of the most interesting parts, I guess, is application examples. First of all, I would like to show you some general installation applications and then go directly to customer applications, which we have already experience with and positive experience with. And in this kind of fields, we have several applications available, which I'm going to show you in a bit. So here we can see the UFS as a the UFS for the protection of one system with one incomer. So here you have your upstream system and your downstream system, and you want to protect, let's say, the downstream system. What's happening here under normal conditions is if the fault is located behind the circuit breaker, the faulty part is switched off by the circuit breaker after detection of the fault by our control unit and the respective tripping of the primary switching element. So, oh, sorry. Here we have the another option with the first one was with the QRU1, and here in combination with the arc guard, if you need additional optical extensions to protect additional panels, as you can see here. And here we can have up to 150 additional compartments monitored by the TVOC and then protected by the primary switching element. Here we see the protection of one system with two incomers. Here the switching system is supplied, for instance, let's say by two transformers, and it has two separate busbar sections. And both, or let's say it has one busbar section, you can protect each part with the left side of your system and the right side of your system with two UFS applications, which can act independently or selectively together. And again, with the help of a TVOC, you can have or monitor up to 150 switchgear panels. The light detection in the CC compartments will only be sent to the dedicated UFS systems. So the red part for the left-hand side and the right part for the blue part for the right UFS. And the green part, this is actually the selectivity functionality here. The signal will be sent to both control units. So let's move a bit faster. Here we have a more complex system, the protection of two systems with one incomer, incomer each. So here, since each busbar section can also be operated independently, one ultra-fast earthing switch has to be considered for each busbar section. The respective PSEs are connected directly to the left hand side bus bar and the right hand side bus bar, and the UFS is activated by the light sensors in the left hand, by the light sensors of the respective rear systems. Another popular solution which we're having here is, especially for the American market, is arc flash mitigation solution for low voltage equipment using the UFS in combination with a current limiting fuse. This one is a third-party tested solution concept to solve the low voltage arc flash problem at the medium voltage system level. And during an actual low voltage arc flash event, what would happen here is that the rear would detect the arc flash and send a tripping signal to the UFS, and which then again would clear or extinguish the arc fault. The fault itself would be cleared then after a specific time by the current limiting fuse, which is here. And thus you would protect your low voltage equipment. And the test results of this third-party test lab showed actually that the incident energy level peak was half cal square centimeters, which is below the stress threshold, which is defined for personal protection equipment. So this solution is appropriate for light and heavy industries, commercial facilities, or medium voltage switches up to 36 kV, or facilities which have medium voltage or low voltage transformers in the range of 750 kilovolt amps to between 750 and 5,000 kilovolt amps. So let's have a look at different customer solutions. Here you can see the ABB low voltage max switchgear, which is type tested with a UFS solution. That one was actually developed in cooperation with ABB Mexico and ABB Germany. And here the primary switching elements are already installed in the panel. In general, we can say that the UFS components for low voltage applications are available for short time withstand currents up to 100 kiloamps for half a second. Another low voltage application would be a data center. Here, as you might already all be aware, is an outage is not acceptable. So what was done here is that we have installed together with an OEM the UFS in a 400 millimeter width panel. And also this solution was type tested in our ABB test lab in the factory at Ratingen in Germany. I think we are running a bit out of time, so I apologies if I'm rushing a bit here. I just want to quickly give you an overview of different installations. Here again, a pulp and paper industry, where we have also a low voltage application due to an arc fault. The customer's switchgear system needed to be exchanged, and here we had 19 609 volt M&S switchgears by ABB equipped with the UFS technology. Here you can see it also installed in a service box kind of application, an extension box, so to say, connected directly to the bus system. And here we have a chemical industry application with ABB Status 1 panel. Here we have the retrofit solution, UFS in top as a top box installation. In general, the top box solutions are basically available for 7 kV 50 kA applications and up to 24 kV 25 kA applications. But here again, we can work up on different kind of solutions based on the customer request. Another application, heavy industries, steel and tubes manufacturer. Here again, the customer was having an outage due to an arc fault, which ended up in a monetary consequences for the customer. Here we have found a solution to install the ABB's a truck solution or UFIS truck solution in a customer's existing panel, as you can see here. Another option is a local public transport. Here again, the customer did not have much space to install any kind of pressure relief duct. So we've been retrofitting or providing, after an arc fault incident, new ABB Unigear panels equipped with and a cable compartment equipped with the UFIS primary switching elements. And that one was actually a more complex system. But here again, we can work on different selective solutions based on customer request. Another installation that was actually a success story for us is in the aluminium industry, where again we had a UFIS as an open installation, as you can see here, equipped with the with 3 PSEs and with a control unit which can detect light and current. Another one was here, again a service box on top of existing panels for a substation. And for everybody interested in offshore applications, we have also experience with offshore. Here is an example for an FPSO, where also the UFIS was installed in some panels. So in case you need further information, please be free to reach out to us, contact us directly or your local ABB partners. Other than that, you can get general information on our websites at abb.com, medium voltage apparatus, or for system upgrades, retrofits. Our colleagues from the service group are happy to help you out with customized solutions. There you go, just to abb.com, medium voltage service, extensions and upgrades. So now let me see what kind of questions we had. Okay. One of the questions asked is, how is this different than a light sensing fault detector within the switchgear? Is it the fact that the UFIS directly shorts to ground instead of triggering a traditional breaker to open? Basically, yes. What's happening here is that the UFIS can detect, in combination of current and light sensing, and with the help of our control unit, can detect the fault much faster than your conventional breakers. It will ground the short circuit in less than 4 milliseconds. So basically your main benefit is the time aspect here before any heavy damages can even apply to your system. Okay, and so there's another question, sorry, what would the use of the UFIS reduce the cal square centimeters to? Well, as before mentioned, I think you're referring to the example which I've been just talking about with the current limiting fuse. In this example, it was tested that the energy level peak was half cal square centimeters. Another question. Does the UFIS also trip the breaker while shorting to ground simultaneously? Well, it's in one of the slides where I've been showing the simultaneous tripping operation. There you could see that it's optional. You can also give a tripping signal to the circuit breaker after the UFIS has tripped for the fault clearance. Can the unit be repaired, or it should be replaced after every reuse? Yes, this is a one-shot device. It has to be replaced after it has tripped. Does this relay on the upstream protective device rely on the upstream protective device to trip after grounding the system? Well, after grounding of the system, your circuit breaker would take over the rest for fault clearance, so your conventional protection system will take over. Another question about arc flash analysis. We have different group, experts in our group available who are doing arc flash analysis, and I'm not sure how it's done in the US, to be honest, but we can provide you some further information on that one. And if you are interested, I can share with you respective contacts who can give you more details on that one. And in ABB, in our distribution solutions, in Germany itself, we are not doing the arc flash analysis. We have other departments doing that for us. However, for all who are interested, now we have the possibility to do arc flash studies with UFIS and EasyPower, just on a side note. What is the typical cost for PSE if needing to replace after each fault? It's usually one third of the initial total cost, the spares you mean, I guess. And it is recommended, in fact, to order one set of spare in order together with one kit in order to go directly into operation again. But for detailed information, please feel free to reach out to reach out to me or to your local ABB partners, so I can provide more information on that one.
Tansu, I think that's the end of our question list and our time slot. Thank you very much for the presentation and the material.
Thank you.
Anything that we're not able to cover question-wise, we'll be able to follow up on email after the session. Thank you, everyone, for attending.
Thank you, everyone, for attending. Have a good day ahead. Bye-bye.